Here, I will try to explain the very complicated linear algebra for PCA. So I'm going to divide this into three parts. In the first part, which is this part, I'm going to explain the basic notations, the basic linear algebra matrix operation, in case you are not familiar with those. And in the second part, I'm going to explain how to apply these to get the main equation for PCA, the projection equation. And in the last part, I'm going to talk about briefly how to do Lagrange multiplier to actually do the optimization. So let's get started with part one, which is just explaining what's the basic ideas, what are notations. So first we have a matrix X, the matrix for the data set. So each data point, say x1, is the same as before, x11, x12, until x1m. So you can think of these, for example, as pixel intensities for an image, and there are m pixels. So, and this is one image, x2 is another image, and so on. So here we have x1, 1, x12, x13. So one single row is one data point, and the second row is another one, and there are n of them. So this matrix is a n by m matrix. So given that xi is basically this xi1, xi2, and xim vector, so this mean is basically x11, x12 until x1m plus the second one, x1, I mean x21, x22 until x2m, and add the third one, so on. Add all of them up, basically means this plus so on, and divided by n, you'll get this mu hat. Mu hat is not a number, it's a vector. So that vector is mu1 until mu m. So it's a 1 by n vector. So the last and most complicated part is the covariance matrix. This sigma hat is the estimated covariance matrix. So the important part is what is this and this. So xi looks like something like this. Mu looks like that. So they can be subtracted firstly. So I'm going to call the difference z, and z will be a vector like this. z1 would be mu I1 subtracted by mu1, and z2 will be xi2 subtracted by mu2, and so on. So this is until zm, and then it is multiplied by z1, z2 until zm. Transpose. Transpose is just make it horizontal vector or matrix. So remember this from the sample midterm, or actually one of the actual midterms. This product is not this column multiplied by this row. So it's not dot product. When you are doing matrix multiplication, you always do row multiplied by column, and row multiplied by column, row multiplied by column. So what you actually get is the first element is z1 squared, sorry, z1 squared. The second one is z1, z2, z1, z3, and so on. And the second row is, again, row multiplied by column, row multiplied by column. So z1, I mean z2, z1, z2 squared, z2, z3, and so on. But at the end, what you have is basically a m by m matrix, and it's for each one of the data points, and you're adding them up. So basically, you add up the one for x1, you get an m by m matrix, and then you add up another m by m matrix for x2, and you add all of them up, and then you divide it by n at the after that. So some people divide it by n, some people divide it by n minus 1. So I think dividing by n means it's the maximum likelihood estimation. And since this is an estimation from from the data point, so you can do different kinds of estimation. So 1 over n is the maximum likelihood estimation, and this 1 over n minus 1 is the unbiased version estimator. So again, either n minus 1 or n is okay. And basically, you add up all of these matrices, so the resulting thing will still be a matrix. So it's a m by m matrix. And in particular, diagonal entries are sigma 1 squared, sigma 2 squared, until sigma m squared. And the off-diagonal entries are covariances that we're not interested in. So these are the basic notations. And here we also normalize it so that the notation is not that complicated. So basically, we want to simplify this so that we don't have this mu hat. So the very simple way to read this, I think this is actually abuse of notation. So don't look at it, look at it this way. Just think of mu hat, setting mu hat to be 0. So that's basically normalization. So change x so that mu hat is 0. So that's called normalization. And after you normalize, if you look at this expression, these two will be 0. So the remaining thing is this expression. So the next piece of algebra is why is this thing equal to this x transpose x? And this is x transpose. This is x transpose x. So it's not the same. So we'll start with this. We'll actually calculate both and compare. It turns out they are the same. So first, remember x is x1 transpose and x2 as a column, as a row, until xn as a row. So x transpose x is x1 as a column, x2, x3 until xn, not m. And then multiply it by x is again x1, x2 until xn. So again, remember when you are multiplying matrices, never do column multiplied by row. It's always row multiplied by column to get the first number here. And the row multiplied by the second column to get this. So we're going to do a simple one. We'll just calculate this particular entry for this and compare with the other one. So here, so what this number is x11. The same number here is also x11, so it's squared. And here, this number is x21. And also, when you are multiplying this and this, you get x21 as well. So it's this plus this. So x11 squared plus x21 squared plus x31 squared plus so on. And of course, you are dividing by 1 over n minus 1 at the end. So this entry is basically the sum of squares. If you look at this, what is xi? Xi is xi1, xi2 until xim, and it transposed is xi1, xi2 until xim again. So note that this thing again is the same thing as what we had before. Here, it's not dot product. The result is a matrix. So in particular, this entry is xi1 squared. This entry is xi1, xi2, and so on. So we're not really interested in any other entry. We only care about this one. So now for each one, it looks like that one squared, and you are summing them up from 1 to n. So that particular entry on the top left corner of this matrix, so it's just the one for x1, add the one for x2, and so on. We only care about this entry here. For x1, this is x11 squared. For x2, this thing is x21 squared and x31 squared. So you can see the pattern. And if you compare this thing and this thing, they are the same. So again, you can do the same thing for this entry here, which is this row multiplied by this column, and you can do the same thing for the sum. Basically, you only sum up these values for i's 1, 2, 3, 4, and 5. Again, you'll get uh, the same value here. So if you compare all the entries, you'll see that these two matrices, one matrix from this expression and the other matrix from this expression, they are exactly the same.